Okay, we'll go ahead and get started. Can everyone see the slide and hear me okay?
Yeah.
Thank you. So what we'll do today is we'll start chapter 14, which is chemical kinetics. And we'll talk about that for about 20 minutes or so. And then we'll move on to the quiz, which is on chapter 13. The other thing I wanted to mention is, we've had some snow ice type stuff this week. I think that's predicted for next week also. If we do have bad weather next week, we'll still have class. It'll just be through Zoom. Okay, so let's talk about kinetics. So when we talk about kinetics, what we're talking about is the speed at which reactions take place. And so this reaction rate is what we're interested in understanding when we have different chemical reactions. Now, one thing about it is when we've been writing chemical reactions, we would write the reactants on the left-hand side of the equation and then the products on the right-hand side. And so when we write it that way, we just make it look like it's just a simple going from those reactants to those products. And quite often it's not that simple. There's a bunch of intermediate steps in between getting from the reactants to the final products. And so if you were to write out all of those steps in between the beginning and end, that would be called a reaction mechanism. And so like in organic chemistry, for instance, if you take that, that's all about understanding reaction mechanisms and things like that. So one of the things that we're interested in chemical kinetics is understanding the rates of reactions, not only of the whole reaction, but also those intermediate steps as well. So when we talk about reaction rates, there's four things we're going to discuss that can affect that the reaction rate. And that's the rate, whether it's the overall reaction or the steps in between. And one of those is physical state of reactants. Another is the reactant concentrations. The third is reaction temperature. And the fourth is the presence of something called a catalyst. So this morning, we'll go into a little bit more detail of what we mean when we talk about these four areas that affect reaction rates. So with respect to the physical state, we usually think of reactions as being homogeneous or heterogeneous. And if there are homogeneous reactions, then what we're simply saying is that all the reactants are in the same phase. In other words, it's either everything is a gas or everything is a liquid. And in general, when things are in the same phase, those reactions are a little faster than what we would call heterogeneous reactions. And in a heterogeneous reaction, as you might imagine, the reactants are not in the same phase. And usually what you're talking about is you have a liquid and then you have a solid. And so one way you can kind of speed up those heterogeneous reactions is to take the solid and increase its surface area. So in other words, more exposure. And that can be done by making the solid into a powder rather than it being just a chunk of something sitting in the reaction vessel. The reason why the physical state matters is that for reactions to occur, the reactants have to collide. And when they're in the same phase, for instance, if it's all gas or all liquid, you have things moving about more freely. And so if they're moving about more freely, then there's a greater chance that the reactants will collide and then have the potential to react. When you have one that's a solid, it's just kind of sitting there, and if it's a gas phase or liquid, you have things moving around in that matrix. But the solid is just kind of sitting there, so you don't have as much movement. Concentration, reactant concentrations, the more concentrated the reactants are, that usually means you increase the reaction rate. And once again, that's simply because if you have more molecules in your container, then you're more likely to have collisions to occur between those molecules. So if you have more concentrated reactants, that means you have more of those reactant molecules in your container. And then as they're moving about, there's a greater chance that they'll have a collision. And once again, you need those collisions in order for a reaction to occur. So typically increased concentration of the reactants means increased reaction rate. Temperature is the third one that we mentioned. And in general, you increase the temperature and the reaction rate will increase. And this is because the kinetic energy of the molecules, that's related to the temperature. So as you increase the temperature, the kinetic energy increases. So you have molecules moving around faster. If they're moving around faster, there's a greater chance for collisions. And so that increases if you have more collisions, and that increases the probability of the reaction occurring. And also because if the temperature is increasing, you've increased the temperature, you've put energy into the system, and so the energy goes into those molecules. And so now the molecules have a little more energy they'd have than they would have at the lower temperatures. So what you see so far is that all three of these things, what it does is it increases the likelihood of the reaction occurring because it increases the likelihood of the molecules colliding. And then the fourth area is presence of a catalyst. And so the catalyst is simply something that you put into the reaction to increase the reaction rate. But the interesting thing about catalysts, they don't show up in that balanced equation. So in other words, they typically aren't used up. Now, catalysts can become what's known as fouled. So in other words, their ability to catalyze the reaction can be negatively impacted with time, but they don't become part of the reaction per se, in that when we think of, we write our reactants on the left side of the equation and on the right-hand side of the products. And so those products, the atoms that are in those products are reflective of the atoms that were in the reactants. Whatever the catalyst is, those atoms don't show up in any of those products. So that's what we mean by it doesn't get used up. It doesn't react per se with the reactants. It just improves the reaction that's going on. What the catalyst does is it usually impacts some of those intermediate steps. And it may only impact one intermediate step. If there's multiples, it doesn't necessarily impact them all. And so what that does usually is it allows you to move a little quicker through one of the intermediate steps as you get to your final products. Now, we'd said before that the reactions tend to go a little better when everything is in the same phase. Catalysts are a little different. Catalysts can either be heterogeneous or homogeneous. And so quite a few catalysts are metal related, and those are usually heterogeneous catalysts where you literally have little pieces of metal in there and they're catalyzing the reaction. And you think about that, metals being a good catalyst. We know metals like to donate electrons, and so donating those electrons can help with some reactions. There's other catalysts that are homogeneous. So if it's a solution, liquid solution that you're working in, the catalyst is a liquid as well. So it just kind of depends on the type of catalyst. So there's both on there. As we said, the reaction rates depend on having collisions between the molecules. So we're trying to react two different compounds together. For them to react, they have to have a collision there. And so anything that we can do to increase that frequency of collision, that will increase the reaction rate. And so that's where the temperature, the concentration, all those things we talked about feed into that, increase the number of collisions between the molecules, and we'll get a higher reaction rate. So just because two molecules collide, though, doesn't mean that you're going to get the reaction or that you're going to get the reaction that you want. So first of all, you have to have the collision. That's step one. Then the next thing is it has to occur where you have the right amount of energy to break bonds. Remember, we said that to break bonds, you have to put energy in. So that collision must happen in a way that there's enough energy that gets transferred into the bonds to break them. And then the third thing that needs to happen is that the molecules have to be oriented in the correct way when they collide, so that the bonds, that you're breaking the right bonds and then you're forming the right bonds in the right location. So we do things to increase the frequency of collision, concentration, temperature, stuff like that. And that usually leads to a higher reaction rate. But just the collision by itself isn't enough for the right reaction to occur. And so whenever you do a chemical reaction, you always, and I think we've talked about this in the past, did some yield calculations last semester, and maybe you get 85% yield of the product that you're looking for. Well, 15% other stuff is because you didn't get the right reaction occur. So you have some impurity or something like that. And so one of the things with these reactions is you're trying to increase the reaction rate, but you're also trying to make sure that you're making the right material as well. So what do we mean when we talk about reaction rate? And reaction rate is simply the change in concentration over a period of time. And so it's signified by this delta, and delta is that little triangle. Delta of the parentheses there, or the brackets, that means molar concentration. So it's the change in the molar concentration with respect to the change in time. So the small t represents time, and time can be in seconds or minutes or whatever unit you want. And so that rate is, all we're saying is, how is the concentration of whatever it is, and it can be a reactant or a product, how is that change in the concentration of that compound, how is it changing over a certain amount of time? And so there's typically three ways that we talk about reaction rates. We talk about an average rate. So that would be the rate if we did measurements over the course of the whole reaction. Maybe the reaction took 30 minutes and we took a measurement every 5 minutes. We would take those numbers and then we would average them, and that would tell us what's the average rate over the course of the whole reaction time. The instantaneous rate is the rate at each of those points that we measured. Okay, and we'll talk in a moment about how we do that. And then the initial rate is the rate at time zero. With reaction rates, they go down with time typically. And so while you can do average rates, you're more likely to do instantaneous rates, and then initial rate, because that's typically the highest rate. That's the one that people are often interested in. So let's take a look at an example here. So we have butyl chloride, which is C4H9Cl, plus water to give us butanol, C4H9OH, plus hydrochloric acid, HCl. And so what we can do is we can calculate reaction rates for the reactants or products. And down below, we have an example of what that rate would be for butyl chloride. And I want to point out a couple things. One is we see there's a negative sign in front of the delta symbol. That's because butyl chloride is one of the reactants. So as time goes on, that number is going to go down. That concentration is going to go down. So whenever you write a reaction, try to find a rate for a reaction, the reactants have a negative in front of that delta, and the products, in this case, the butanol and the HCl, would not have a negative, they'd have a positive. So we have a negative in front of that change in concentration of the butyl chloride divided by a change in time. And here's an example of the kind of data you would see if you were monitoring this reaction. So on the left-hand side, we have time. In this case, it's expressed in seconds. So we have values of 0, 50, 100, 150, et cetera, for the time points. Then what we see next is we see the concentration of butyl chloride. That's molarity, moles per liter. And so we have start at 0.1 molar, and then we see it drop down to 0.09, 0.08, et cetera, on down till we get eventually to 0. And then over on the right, we have the calculated value for what the rate of the reaction was. And we see it starts out at 1.9 times 10 to the minus fourth molar per second. And by the end of it, when we get towards the bottom, it's slowed down quite a bit. Now it's 0.560 times 10 to the minus fourth. So that's pretty typical. Your initial is your fastest rate, and then it goes down. And why does it go down? Well, one of the things we said it's dependent upon is concentration, and that butyl chloride concentration is going down. If it's going down, then there's less of it. And so that means there's less molecules, less likelihood of collisions happening. And so think the rate slows down. Okay, one last thing I want to just mention is how do you calculate those instantaneous rates that we talked about here? So here we had a bunch of rates. How were those calculated? Well, what you would do is you would take the data and you would plot it like you see on the plot here. On the x-axis, we have time, and that's in seconds. And then the y-axis, we have the concentration of the butyl chloride. And so we start out at 0.1 at time 0, and then we plot that concentration as it goes down with time. The way you would know the concentration is that each of these time points, you would sample from your reactor and analyze it to see how much butyl chloride is left. And then that would then allow you to do this plot. If you draw a tangent to any of these points, and you can see two examples here, you can see kind of the yellowish one up top and then the blue one towards at the bottom. You can see how a tangent line has been drawn in each of those cases. If you calculate the slope of that line for those particular times, in the top one, it's time equals 0, and then the bottom one, it's time equals 600 seconds. If you calculate what the slope of that line, tangent line is, that's the rate. And so that's where those numbers come from. The final thing I'll say, a couple things, is one is, I think visually it's a little easier to see in the plot how the reaction rate goes down with time. And I think you also see that it's not linear as well. So we'll talk a little bit more later about what the shape of the curve means. But for now, I think that'll be it for now. Any questions about any of this intro kinetic stuff that I just talked about? Okay, well, if not, then please go on to Canvas and pull up quiz number 2 and go ahead and start the quiz. And I'll see you guys on Tuesday. Thanks.
Thank you.